Okay, as we have defined what does it mean for a finite automaton to recognize a language or a string, let's see some examples on how to determine the language that a given finite automaton recognizes. So, for instance, this one is one of the examples we have seen earlier. Here we have three states, and one of them, sorry, four states, and just one of them is accepting S3. So in order for a string to be accepted, it has to take S0 to S3. And if you look at S3, any input after you reach S3 is irrelevant. You do not go out of S3. So if you ever reach S3 via some string, then you stay at S3. But how do you get to S3? So look at the non-accepting states, S0, S1, and S2. Um, any input of 1 doesn't change the state, but one input of 0 takes you to the next state, S0 to S1, S1 to S2, and S2 to S3. Okay, so this means any string that will have at least 3 zeros in it, irrespective of how many ones you have, is going to be recognized by this automaton. So for instance, 000 will be accepted, 0100 will be accepted, 11110110110011 will also be accepted, right? Because you make three transitions from S0 to S1, S1 to S2, S2 to S3 with any three zeros. And then when you reach S3, you don't leave S3. So you can have more than three zeros. And the number of ones doesn't really affect whether a string is accepted or not. So the language recognized by this automaton is the set of binary strings that has at least three zeros in them. Let's look at another one. Now, this is a little bit similar, but essentially different. Let's see what the difference is. You see, we have the same set of states and the same accepting state, S3, and the initial state is also the same. And from S0, the initial state, again, with three zeros, I move to S1 and then S2 and then to S3. But you see, the behavior when the input is 1 is now different. Of course, when you are in S0, you stay in S0 with the 1. But when you are in state S1, the one earlier we discussed stayed in S1, but now it goes back to S0. So it's sort of a reset. Similarly with S2, S0 takes you to the accepting state, but an input of 1 takes you to the initial state. So it's sort of reset. So what this means is in order to reach S3, you need three consecutive zeros. So 0, 0, 0 should take you to S3. If you have a 1 in between, okay, you come to S1, but then it takes you back to S0. And the remaining two zeros is not sufficient to take you to the accepting state. So for a string to be accepted by this automaton, it has to have a consecutive triplet of zeros, so in the form of this. It can appear anywhere in the string. So for instance, 110001011100000011 will be accepted. 000 by itself is going to be accepted. 00 is not going to be accepted, or 1010101011 is not going to be accepted. But if you add a triplet of zeros here, for instance, it will be accepted. So it needs a consecutive triplet of zeros, this finite automaton. So the essential difference between these two is that the one on the top wants just at least three, and it doesn't require the zeros to be together. But the one on the bottom, it wants consecutive zeros. Let's look at another one. Again, this is from the example earlier. Let's see how this works. The initial state S0 itself is accepting. So the empty string in this case is accepted. And you see now zeros in this case do not change the current state. So S0 with a 0 input stays at S0. S1 with an input of 0 stays at S1. But once the inputs of 1 alternate the states. So with a 1, you go to S1, and with another one, you come back to S0. And since S0 is the accepting state, what this means is for a string to be accepted, it has to have an even number of ones in it, right? The first one will take it to S1, the next back to S0, right? So if you have like 1, 0, 1, 0, 0, 1, then this one will take you to S1, this one will take you back to S0, this one will take you to S1 again, which is not accepting, so this string will not be accepted. If you have another one somewhere here, it will take you back to S0, in which case this is going to be accepted. Hence, this finite automaton recognizes or accepts binary strings that has an even number of ones in them, including none. For instance, 0, 0, 0, 0, 0 is going to be accepted, or the empty string by itself is also going to be accepted, because you are just going to end up in the state S0, the initial state. Now, this is how you can actually come up with the set of strings that a given finite automaton recognizes. How about the other way around? If we are given the set of strings to be accepted, how do we design the finite automata to recognize those sets? Here are some examples or exercises from Rosen. Construct the finite automaton that recognizes the set of all bit strings beginning with 0, 1. So I have an initial state, and I want the first two inputs to be first a 0 and then a 1. So a 0 takes me here, and a 1 takes me to my accepting state. So how about the rest of the behavior? So from S0, a 1 should take me to a state, because as soon as you observe a 1 at the beginning, that string loses any chance of being accepted. So this state is going to be a non-accepting state. Okay, and then again in this state, if I see a 0, then it should also take me to this non-accepting state, because now the second input is not 1. Okay, so these are non-accepting states. And if I reach the non-accepting state, it will not be possible to correct the string, because what I require is the beginning of the string. So I cannot get out of here. 0 and 1 will keep me in this non-accepting state. And the same goes for the accepting state, because if the beginning is correct, I don't care about the rest. So whatever input comes, I stay in the accepting state. So this is the finite automaton that recognizes binary strings beginning with 0, 1. How about the second one that end with 1, 0? Now again, I'm going to have a state which takes me to this next state with a 1, and then with a 0, I need to go to the accepting state. But before the final 1 and 0, I can have any input as I can. So let's say this is the initial state, and any input of 0 is going to keep me here, and any input of 1 in this state is going to keep me here. Now, when I reach the accepting state, you see with a 1, I go here. That means this is a candidate, this 1 is a candidate of being the penultimate bit, and this 0 is a candidate of being the final 0. But then if I encounter another 1, since the string is not ended, then that one becomes a candidate for being the penultimate bit again. Okay, so what if I encounter a 0? Then it should go to the initial state, because now I need a 1-0 pair. Okay, so this is the finite automaton that recognizes strings ending with 1-0. If you like, you can try some inputs with some strings and see that the strings that end with 1-0 ends up in this state, and the others, they end up in either this one or this one, meaning that they are not going to be accepted. And let's look at the other two that contain the string 1-0-1. So now here, I'll come to this state with a 1, and then with a 0 to this one, and to the accepting state with another 1. And of course, in between, if something unexpected comes, I'm going to reset the procedure. And therefore, here you see the final input was 1. So in my accepting state, if I encounter a 0, I'm going to go to this state, because now the running input will be 1-0. And with another 1, I can still go to the accepting state. And what about a 1 occurs? Then you go to this state, so that because the previous one was a 1, so now you have a 1-1, so it cannot be the beginning of a 1-0-1. Therefore, you start the 3 bits 1-0-1 anew. So this should be separated here, like so. Okay, so here in this state, what if a 0 occurs? This means the last 2 bits were 0-0, hence I need to go to this initial state. Meaning that I haven't encountered the first one yet. I'm looking for the first one of the pattern 1-0-1. Okay, so this is the initial state, and with a 0, it stays in itself. So if you start here, if you encounter a 0, you stay here waiting for the first one. If you see it, you move here, and a 1 at this point should keep you here until you see the next 0, which will be the second 0 or second symbol of the pattern 1-0-1. Okay, and at this point, if you see a 0, you need to start all the from the start, and if you see a 1, you go to the accepting state. Okay, and well, if you reach 1-0-1, sorry, so these should not be like this, because it says that contain the string 1-0-1. So as soon as you have 1-0-1 and reach accepting state, you should stay there, because since you have just one instance of 1-0-1, the pattern 1-0-1, the remaining of the string is not really important, because it's already satisfying this definition. And finally, let me put the solution of the last one here. Strings that begin with 0 or with 1-1. So this is your initial state. So with a 0, you are going to go here. Since it starts with a 0, this is going to be an accepting state. And if it starts with a 1, I'm going to go to this state. And this one is going to stay here with the next 0s and 1s, because I'm just looking at the beginning of the string. And with the 1, I come to this state here. And with this, if I encounter another 1, I need to accept the string. Okay, but if I see another 0, then there is no hope, because it will be starting with 1, 0, and there will be no way of accepting this string. So this is my non-accepting state, and I need to stay here because it will not be able, the string will not be able to be accepted with the remaining symbols.